Happy New Year, everybody. Thanks a lot, Vivian, for accepting our invitation to talk at the CosmoVerse series. Vivian, since 2019, is a CNRS researcher based at the Laboratoire Univers Particules de Montpellier. He obtained his PhD in 2017 through a joint program between the LAPTH laboratory in Annecy and the RWTH University in Aachen, working on signature of dark matter models and neutrinos on the CMB. Vivian then joined the Johns Hopkins University as a postdoctoral fellow in the group of Mark Kamionkowski, where he started working on the Hubble tension and the cosmic anomalies, and in particular the dark energy models. Today, he will present the sigma-8 tension is a drag. Vivian, you can start, please, when you're ready.
Yes, thank you so much. Can you hear me? Very
Yes.
good. So thank you very much, Eleonora. Happy New Year, everyone. I think it's the first year. I mean, I know it's the first talk of the year. And thank you for being here, being back from the holidays, and hopefully this won't be, a bad decision of your side to attend this talk. So I'm going to talk indeed about the possibility that the sigma-8 tension indicates that there is some new interactions happening between dark matter and dark energy. I should already put forward that this is certainly not a new topic in itself, but I'm going to try to also advertise something that I believe may have been a bit missed or was a bit under the radar, and that is there may be some connection between dark matter or dark energy transition and the sigma-8 tension. And yeah. So a quick summary of my talk is that first, I'm going to try to argue that the S8 tension is in fact a sigma-8 tension. There is no signs of a low omega m at late times from probes that we have. In fact, not only is it a sigma-8 tension, but it even originates from late time. We have data that seem to constrain models that lead to some sort of power suppression at early times. Then I'm going to talk more precisely on the topic of dark matter, dark energy, and argue interaction, and argue that a potential drag between dark matter and dark energy, which is a model which has a single free parameter, may solve the tension, and there is some sort of coincidence, if you want to call it a new coincidence, or between the amplitude of that drag and the time dependence that makes it such that the drag is active right around the dark matter dark energy transition in order to solve the sigma-8 tension that such as we have measured it so far. And yeah, all right. So just a brief reminder, in case you had forgotten over the holidays, that there is a mismatch between the measurements or the predictions for the S8 parameters based on adjusting CMB data at redshift of order 1100 that favors large value of the S8 parameter, and that measured at low redshift, typically with probes probing redshift below 1, that tend to favor low S8. So this includes, of course, the famous KIDS and DS galaxy lensing and galaxy clustering cross correlations, but also some perhaps less known results from also both power spectrum that's debated. There may be that's not necessarily as strong in tension, and there may be some projection effect in these measurements, but you can see that all of those measurements seem to indicate that at low redshift, we have a smaller amplitude of fluctuation than what is predicted from the lambda CDM model fitted on CMB data. So first, as I said, I want to argue that really the tension is rather in sigma-8 than omega m. This is first attested by what we call the 3x2 point statistics, so the combination of galaxy lensing, galaxy clustering, and their cross correlation, as measured, for instance, here in red by KIDS. You can see that when you do these cross correlations, when you combine these statistics, really the tension is not really in the omega m direction, but rather in the sigma-8 direction. And this is also hinted at the fact that we have very strong constraints on the late time expansion history that constrain the value of omega m to live in the neighborhood of 0.3. And so all of this seems to hint that the tension is rather in sigma-8. You may argue that this is assuming simple lambda CDM-like dynamics at late times, and we may have more evolved time evolution at late times. For instance, here I'm showing the case of a time-evolving dark energy. It's very well known that for Planck alone, time-evolving dark energy is fairly unconstrained. There is what we call a geometric degeneracy between the dark energy parameters and the expansion rate of the universe H0. that allows to keep the CMB most favored, featured scale at the same position. And at the same time, this degeneracy leads to a degeneracy with omega m and therefore with S8. However, as soon as late-time probes of the expansion rate are added in the analysis, such as BAO or Pantheon supernovae datasets, these seem to favor an equation of state of dark energy very close to -1. And the rule of thumb is that the equation of state of dark energy is constrained to be close to -1 at something like the 3% level. So I hope this convinced you that one must really decrease the amplitude of fluctuations rather than play with the background dynamics, or at least play with omega m sorts of dynamics. One needs to decrease the amplitude of fluctuations to decrease sigma 8. But there's still a question that one needs to answer is what scales needs to be affected when we talk about decreasing the amplitude of fluctuation. So taken at face value, one may say one needs to decrease the scales relevant to compute sigma 8. And indeed, sigma 8 is a derived parameter that measured scales around 0.1 H inverse megaparsec. Here in blue, I am showing you the kernel of integration of the matter power over which the matter power spectrum is convoluted, and it peaks around 0.1 megaparsecs. At the same time, in green, I am showing you the supports of scales over which CMB acts, so that CMB measures. And you can see that there is some overlap between the two, meaning that CMB indeed can be used to measure sigma 8. And in principle, what people do is to fit, as I've already said, some model. The fundamental parameters that matters is the primordial amplitude of the power spectrum, primordial tilt, the matter density. And this is done at redshift of 1100, and you predict the value of sigma 8 at redshift of 0. And looking at this, you can say that either you need to suppress scales here in the regime where essentially CMB don't have support, or you need to have some sort of time evolution such that you change the amplitude of fluctuation only at late times. I do want to point out that we have intermediate probes of the matter power spectrum, not only between redshift of 1100 and today, but we have, for instance, CMB lensing, whose kernel of integration spans and peaks around Z of 2. And also we have Lyman alpha data that seems to disfavor, both of those probes seem to disfavor strong suppression of power at early times. And this would favor a late time evolution for the creation of the power suppression. There is another way of looking at the problem is to say that sigma 8 may be a red herring, because after all, the probes that drive the constraints, even though we are always translating the amplitude of the power spectrum at scales of sigma 8, the probes that drive the constraints are probing much smaller scales. In fact, even down to something like 10 H even megaparsecs. So these are weak lensing measurements in particular that probe such small scales. And here in this paper, these authors have shown that if you had some sort of modulation of the nonlinear matter power spectrum, a large modulation that may be created, for instance, they argue by strong feedback from baryons or new physics, that's also a possibility. At small scale, look, the scales are much smaller than the naive sigma 8-like scales that I mentioned, but still you could potentially explain away the sigma 8 tension. So the debate really is it just a small scale issue, or does it also affect large scales? And I would like to argue that we have probes that seem to indicate that it can also affect large scales. And one of the most important probes is the so-called CMB lensing in galaxy cross correlation that is also in tension at large scales. But in the literature, so I want to mention that we have had also galaxy-galaxy lensing has been shown that even on large scales, may be in tension, not as strong a tension, but also in tension. That's debated, and there is some literature about this. Just coming back to this CMB lensing cross-correlation with galaxies, here I'm showing you for the case of DES, but this has been done also for other sort of surveys, for instance, for BOSS and for DESI. Here I'm showing you the redshift distribution of the galaxies measured by DES. compared in gray with the kernel of the lensing of the CMB. So that would peak, as I said, around redshift of 2, but as a very broad kernel. And here you have the kernel of integration for the weak lensing of those galaxies. And the key is that when you cross-correlate galaxies with CMB lensing, what you're doing is that you're picking up signals at low redshift and on fairly large scales, because the maps that we are using, that those people are using, which are usually the Planck maps, or SPT, but Planck dominates the signal, I believe, or at least dominates, is mostly at high signal to noise on large scales. So you're picking, what I'm trying to argue is that by doing this, you're essentially picking up signals at late times and on fairly large scales. And what you do when you compute within the lambda CDM model constraints on sigma 8 and S8, you can do what's called this 5 times 2 point statistic. So these 5 times 2 points combine galaxy lensing, galaxy clustering, and the cross correlation with CMB lensing. But it does not include the auto-correlation of the CMB lensing, what we usually call the Planck, if you want, lensing power spectrum. When you do that, they've realized that you get this lower value of sigma 8, and very similar results are obtained in this paper, to be compared with the primary sigma 8 values from the primary, sorry, the CMB primary sigma 8 values. Here you see the tension is at the level of 2 to 3 sigma, depending on what data you're using. And this can also be compared with the standard CMB lensing in gray. The standard CMB lensing, which again probes redshift of order 2 and higher, does not show signs of a low sigma 8. And in fact, when you combine the autocorrelation with this cross correlation in this 6 times 2, it drives back up the value of sigma 8. So what do we learn from this? We learn that the lensing autocorrelation favors large sigma 8s, so at redshift order 2, but below, at redshift of order 1 or so, we do see a power suppression. So this would mean that indeed the suppression had to leave the CMB lensing, so to say, unaffected and be generated at late times, and even potentially affect large scales, since these probes are mostly large scales. So how can we do that? So let me just go back to the basics briefly, looking at the growth of CDM density perturbations, the linear perturb continuity and Euler equations for CDM perturbation, which is what drives the growth of matter perturbation. So we have, of course, the perturb continuity equations for the over densities and the Euler equations for the bulk velocity, or the divergence of the bulk velocity. And we have the metric potential. And what we know is that for pressureless, collisionless fluid, such as dark matter, there is no scale dependent in the growth. Like any scales will grow once it's within the horizon at the same rate. So we need to find ways to break that scale independence. The first way to do it is to say, what if there is pressure in the fluid? And you can so include a non-zero pressure, and which means reinstate an equation of state and a sound speed. And combining this equation, we can write a formal equation driving the growth of perturbation on small scales. This is exactly what happens for neutrinos. And you know that for neutrinos, when the mode is well within the Jing's length, when the mode is greater than this Jing's mode, it will experience damped oscillations like this. Eventually, neutrinos will become non-relativistic, so it's going to start growing again like standard CDM, if you wish. But by doing this, we have found a way to break the scale independence. Of course, neutrinos of large mass that would be required to resolve the sigma 8 tensions are completely excluded. As I've already mentioned, they would lead to a early time sort of suppression, and we have probes that are unhappy with that. But one way to generate a late time suppression, and here I'm just briefly, shamelessly advertising another work, is to say, what if dark matter decays, and such that at late times, if you wish, it generates this sort of neutrino. So here it's a model where dark matters decay into a warm dark matter sort of component and a dark radiation component. You have two free parameters, the decay rate and the branching ratio. And the branching ratio also sets the velocity kick received by the warm dark matter particle. And in this sort of model, you can, at early time, when there is no decay happening, you have essentially no suppression, and at late times, you dynamically generate a very large suppression. And in this sort of model, you can explain a low state, or at least the data are in agreement at something like 1 sigma. However, in this model, of course, these are just free parameters, and there is no connection with dark matter, dark energy transition whatsoever, or even the time scale is just completely arbitrary here. So let me move on to possibility of having new interactions in the dark sector. And again, before talking about dark matter, dark energy, I wanted to just briefly mention the fact that people have also studied the possibility of having dark matter, dark radiation interactions. And I want to argue that these are somewhat disfavored by the data, again, because of the fact that there are data that constrain suppression of power at early time. So there is a large literature around dark matter, dark radiation. And one generic framework capturing most of those models, not all, but most of those models, is this so-called effective field theory of structure formation, and in which the interaction between dark matter and dark radiation, which will look very similar to what happens for dark matter and dark energy in the model of interest, is such that there is a new drag term, some sort of Thomson interaction, if you wish, or not necessarily Thomson, but some sort of drag term between dark matter and dark radiation, that will slow down the growth of perturbation because dark matter will fall less quickly, if you want, inside of gravitational potential. And the strength of that drag term is typically parameterized by some amplitude plus some power law. And the additional free parameter in this sort of model would be the amount of dark radiation that you have or the temperature of the dark radiation. And what matters here is simply to show that as you increase the drag term, the drag amplitude A dark, you may create stronger and stronger suppression. And indeed, when you confront these models to data, in particular, when you confront this model here in the specific case where you do not have a power dependence, in fact, a power law dependence with redshift, you find sleeves of parameter space for which you may explain very low values of sigma 8. However, what these models are facing is also strong suppression from early times, because these models are imprinting the suppression already from early times. And so they tend to be excluded by Lyman alpha data and potentially also by CMB lensing. So we have this scenario. So now we are in this situation where we have data that mostly probes low redshift showing a tension in sigma 8. And coincidentally, these data at redshift below 1, in fact, are also probing the time at which we transition from a universe that is dark matter dominated to a universe that is dark energy dominated. So what we're trying to ask is a question, or a generic question that one may ask is there some sort of connection between this S8 tension that only affects low redshift and the transition from dark matter and dark energy? And more generally, can the S8 tension indicates a connection between dark matter and dark energy? So models leading to interaction of dark matter between dark matter and dark energy have in fact already been suggested in the past for a while now, a very long time, to explain cosmic coincidence problem, which can be summarized in one sentence as saying that why is the dark matter and dark energy, are the dark matter and dark energy abundance so close to one another if they could take any value in principle? And in these models, what has been found is that there are scaling solutions where in fact the dark energy density is just a fixed fraction of the background energy density of typically of dark matter at late times. And in fact, those scaling solutions are even attractor solutions in some cases. So the way in which people have modeled that in a phenomenological way is to assume a coupling at the level of the equation of motion, some sort of flux of energy between, or momentum between dark energy and dark matter. And a potential, one of the models that works very well and shows this attractor solution towards a scaling solution is a coupling that takes this form when we have some rates of interaction proportional to the Hubble rate and to the dark energy density and the cold dark matter density. In that case, the solution of the evolution equation show that there is the ratio of the cold dark matter and the dark energy density is going to be this constant number in the far past. Eventually is going to change once maybe dark radiation is going to dominate or so on. radiation is going to dominate and so on. And then eventually, when matter starts to dominate again, may reach again a constant value. And then the problem is then completely set by the strength of that interaction. It's psi parameter, and in principle, you can compare this model to data and constrain the values of psi. And of course, this sort of model is phenomenological, but similar behavior have been found in actual realization through dark matter and dark energy scalar fields that are coupled. And beyond just looking at the cosmic coincidence problem, dark matter and dark energy interactions have been studied in order to look for their impact on cosmic tensions. And one of the models that have been, and in principle, in general, dark matter, dark energy interactions have a rich phenomenology that could explain cosmic tension. And a well-studied example, for instance, by Eleonora and others, is a model where the coupling that I mentioned before, this flux of energy and momentum that I mentioned before, is now given by these sorts of form where you have a coupling constant and the Hubble rate again, and now you only couple to the dark energy equation of states. The dynamics is such that you're going to change the time evolution of the energy density of cold dark matter and dark energy, and essentially you're going to create this modified equation of state for dark energy and some additional term for the evolution of dark matter. And of course, you can also modify the dynamics of linear perturbations. And Eleonora and others have shown that if you confront this model to Planck plus some information about the Hubble parameter, you may in fact very well explain the Hubble parameter as measured by shoes with some strengths of interaction. Unfortunately, because of these models have deviation away from flat lambda CDM at late time, there are constraints from BAO and Pantheon applying on them that once you add BAO and Pantheon, it's not as clear that you detect this non-zero interaction. In the context of sigma 8, that's also been studied by Matteo Luca, which have shown that you also have a degeneracy with S8. That, in fact, also I think in this paper this was pointed out, but let me just show this figure here, where you could reach very low value of S8 for large value of that interaction rate. But unfortunately, as you can see, the interaction rate is not detected, and that's due again to the presence of those late time data measuring the expansion rate, BAO and supernovae, that prevents deviation away from flat lambda CDM in a significant manner. So the background dynamics is tightly constrained. So the question now is, could we do away with a model that just plays with modifying the linear perturbations? And that can be done by considering, instead of a coupling between energy densities, a coupling between the 4 velocities of the dark energy and the dark matter. So we replace this coupling, this phenomenological coupling that I introduced before by this one, where it's just some sort of interaction that mimic an elastic scattering between dark energy and dark matter, where this interaction rate here may be a constant, maybe not, depending on the model that you have. In our case, we're going to study a constant. And in fact, these models have been studied in the past, and even it has already been shown that such models may explain a low sigma 8, and I want to discuss that now. So the dynamics of such a model is simple. So again, you modify the Euler equations in only the Euler equations. So these were the standard equations. You now add this Bragg term, which resembles what we've seen for dark radiation and couples dark energy and dark matter. And once you work out things, you realize that in this case, there is some small scale time dependence entering just from how things are defined. But at the level of the energy moment of the stretch energy tensor, what has been introduced, of course, is a constant interaction rate. And the continuity and Einstein equation in these models are identical to standard lambda CDM. So let me discuss what the dynamics look like in this model. So for a constant interaction rate at the level of the stress energy tensor, and W that is close to -1, again, just because we have to allow for, we have to fulfill the constraints coming from late time data, we find that the power suppression grows with time. So in the late time, in the far past, it's negligible and it simply grows with time. And when gamma is over H, is of order h, or gamma over h is of order 1, is when the interaction rate essentially become effective, and it can slow down the falling of dark matter into gravitational potential and lead to this power suppression that is time dependent. And just to give you numbers, for interaction rates that are of order h naught times the critical density, which are the two only numbers that we have really in the game at play here, this happens right between the dark matter dark energy equality and the start of acceleration of the universe. So this is not very important in itself. It's just to give you an order of magnitude of what are the relevant numbers in this game. But what is interesting is that as long as W is fixed to -1 or close to -1, and again, this is enforced by the data in any case, this amplitude gamma that I've introduced is the only free parameter in the model. It's the only free parameter that sets the dynamics. And in particular, it's going to drive both the amplitude of the suppression that you're going to get and the time dependence. What that means is that if you had a larger interaction rate, you have at the same time a larger amplitude today of suppression, and the suppression started earlier, way before, in fact, the redshift for which we see any sort of suppression. On the other hand, if the interaction rate was much smaller, in blue, then the interaction would have started much later and lead to a much shallower interaction rate, much shallower suppression. And so what I'm going to try to argue now is that because we have measurements of the amplitude of fluctuation at late times, we have measurements coming from measuring sigma 8, from the SA tension, if you wish, we know by this model tells you that the interaction must have switched on exactly at this curious time of the dark matter dark energy transition, and by construction is not going to affect earlier times. So when you confront that model to the data, you find this. First, if you don't include any information on the amplitude at late times, unsurprisingly, you get very little constraints. This is what you get here. The constraints are mostly driven by this F sigma 8 data, which have fairly large error bars. And once you include some knowledge about S8, or about the amplitude, you pinpoint that the interaction rate that is required is exactly around h0 times rho c. Again, this value specifically is not important. What matters is that this means the interaction rate is going to be active, or the interaction, is going to be active right around dark matter, dark energy transition. You may ask what happened if I free W, because this is very natural in this sort of model. And just to convince you that that does not matter, because we have strong constraints on W again. So even if you free W, the model that favors values of the interaction rate that are such that the interaction switches on right around dark matter, dark energy transition. So this is what is shown here in red with the 68% interval. Again, I want to say that a priori, the amplitude was completely free to be whatever it wants. It could have been that it was very large, that the amplitude that we measure, the suppression that we measure was extremely large. And if it had been very large, then this model would have predicted that the suppression would have started at much earlier time. On the other hand, if the suppression was much smaller, and again, it could have been anything, this model would have predicted that the suppression starts at much later time. And because we have such an amplitude of suppression, it has to start right around the transition from dark matter and dark energy. So this would indicate, is there some sort of new coincidence, if you wish, between the sigma 8 tension, or the amplitude of the suppression, and this transition? And potentially, is there a connection with these models that were able to really resolve the cosmic coincidence that already exists at the background level? So this is an open question. This is just something that we point out. It's not clear, as I'm going to argue, that we can build simple scalar field models at least that leads to these properties. But this is something that is open for future work. Before that, just mention that we have clear signatures of the model. Even if you don't necessarily lag this model, at least you can probe it and exclude it. The clearest signature, of course, I've already insisted a lot on this, is the time dependence of the suppression. For instance, looking at redshift space distortion, For now, these are not extremely constraining, but with a survey like DAISY, you might be able to probe this power suppression and this time evolution of the power suppression. I should say, sorry, that this, of course, assumes scale independence. By construction, we have introduced some level of scale dependence. So this is to be taken with a grain of salt. There has been, in fact, already in the past, some n-body simulations that have been produced for a very similar model of dark matter, dark energy, elastic scattering, and that indicate that there may be additional non-linear effects that are quite strong and that affect the halo mass function and the concentration function that would, if you want, give additional handle on the model. Another very pristine signature of that model that was put forward in the past is the fact that you are going to create a relative velocity between dark matter and baryons. And that's because you're coupling dark matter to dark energies, but you're not in this simple way, in this simple model, coupling baryons to dark energy. So in the standard WCDM sort of model, there is no relative velocity at late time. So the power spectrum of the velocity for dark matter and baryons is identical. But once you include this coupling, of course, the velocities of dark matter is going to want to couple to that of dark energy. And as you increase the coupling, here the alpha parameter is identical to the gamma parameter, you may strongly couple even dark matter and dark energy. So let me just recall that the situation that we are in, the data favors something that looks like this model here. And so you can introduce a scale-dependent bias between the dark matter and baryon relative velocity. This can lead to signatures in the galaxy power spectrum. In particular, just recently, the group of Jimenez have shown that by measuring the dipole of the galaxy power spectrum, you may probe the existence of such interaction. And using an SKA-like experiment, doing a forecast, they've shown that a model that can explain the sigma-8 tension may be detected by something like SK. Of course, this sort of signature extend to much smaller scales even, so you can expect signatures at galactic scales. You can affect tidal streams, or you can affect the rotational velocity of stars and so on. These are effects that you can imagine studying in the future. The last point that I wanted to bring up is, can we generate a coupling of dark matter and dark energy, for instance, through coupled dark matter, dark energy scalar field models? And how can we generate a pure momentum exchange from first principle? And this is a question that has been studied in the past already, at least, again, in the context of dark matter and dark energy scalar field. And these authors have classified the Lagrangian describing interaction between dark matter and dark energy scalar field into three types. And they have identified that we have what they call the type 3 models that only involve momentum exchange. So in general, you can write the Lagrangian as a function of the number density of dark matter, the kinetic term of the scalar field, a coupling between the gradient of the scalar field and the force velocity of the dark matter, and the scalar field itself. So those are a very generic forms of the Lagrangian. And in this type 3 model, you split this Lagrangian into a function, so the coupling between a function that includes the coupling between the scalar field, the gradient of the scalar field and the force velocity, and a function that is purely a function of the number density of the dark matter. And that function, for instance, is going to set the energy density of dark matter, the sound speed of dark matter, etc. And in a recent paper, in fact, they've studied such a model where they specify a specific form for that Lagrangian that fulfill a type 3-like model where only momentum exchange is at play. So you have a canonical kinetic term for your scalar field. You have some potential that they've taken to be an exponential potential. And they've modeled the coupling between dark matter and dark energy that is at the level of the form velocity of the dark matter with some power law, simple power law. That's arbitrary. You could imagine more complicated model, but that's a start. And what they show is that the results, in fact, are very similar to what you get in the phenomenological model. The interaction is favored once you include the low S8 data. And this is what's shown here in green. The full analysis include low S8 data, and they also find a non-zero interaction rate at large significance. Here I'm going a little bit fast because it's not clear in reality that the simple constant interaction rate that I introduced earlier, the elastic scattering, if you wish, can simply be mapped onto this phenomenon, onto this more realistic framework. This is actually a discussion. In fact, at the end of the day, it essentially boils down to how what function you're going to choose for that and whether it's realistic or not. But there is discussion around this in the literature. But in general, what we try to point out here is that there may be some new coincidence, if you wish, at the level of perturbations now, in a sort of cosmic coincidence at the level of perturbations, that may indicate that there is also dynamical solutions to the cosmic coincidence problem. So I'm reaching the end of my talk. Let me summarize. So I've tried to argue that the SA tension first is really a sigma 8 tension. There are no signs of low omega m at late times. In fact, the sigma 8 tension originates even at late times. We have data that constrain strongly models with early time suppressions. I've mentioned Lyman alpha, and I've mentioned lensing of the CMB that favors fairly high values of sigma 8. So the suppression must originate at late times, below 1. I've shown that there is some sort of curious coincidence between, in a model of drag between dark matter and dark energy, there is a single parameter can solve the tension, and by measuring the amplitude of the suppression, we have fixed the time dependence of the interaction, and this favors an interaction occurring or taking form right around the transition between dark matter and dark energy, and naturally explain why you don't have any signatures at large redshift, and why lensing and Lyman alpha would not see any sort of suppression. So this indicates that perhaps there is a connection between sigma 8 and the dark matter and dark energy domination. Currently, it's more of a new coincidence than a true dynamical explication, but that's to be studied further. So in fact, the model building of dark matter, dark energy, coupled dark matter, dark energy scalar field exists, and there's large literature about it, but it's not clear that the pure elastic scattering model that I've introduced can be mapped into that framework, but even more realistic framework, more realistic model work to explain the sigma 8 tension, although it's not sure that the connection with the cosmic coincidence exists in that case. And whether or not you like this model, be aware that this model can be looked for with new surveys, so we'll be able to rule it out or confirm it. For instance, by measuring the time dependence of the power suppression, or by looking for effects at the level of velocities, for instance, by measuring the galaxy power spectrum dipole. And thank you very much for your attention, and again, Happy New Year.
Thank you, Vivian. Thank you so much for the great talk.
Thank you.
Okay, do we have any questions? Bozena, please.
I have two questions, but I'm not absolutely sure that it's really related to your topic. So the question is whether they are related to the topic or not. The first question is that both are about nearby cosmology. I mean, not even cosmology. First point is the missing dwarf galaxy issue. I think when now people introduce intertidal interactions, modeling a bit better, whatever, they still cannot account for the expected number of dwarf galaxies around larger galaxies. So I'm not sure whether this is the same manifestation of what you are saying, but at the smallest scales.
Right. So no, so that's a good point. So first, I think now the missing satellites problem and so on is fairly debated, because it may be due to these small satellites not actually activating. You can't see them essentially because there is no star formation in them. But these guys, even there are models of dark matter, dark radiation, I believe, maybe dark energy, but that I'm not fully aware of that literature interaction that would lead to a phenomenology where you suppress powers and therefore suppress the number of dwarf galaxies. That's for sure. But I think they may need some sort of velocity dependence in the interaction rate in order to fulfill some constraints and so on. But I believe more generally, you're not wrong that the sort of signature that I'm looking for on cosmological scales, this is what I was very briefly mentioning, is going to lead to signatures on galactic scales and on the halo mass function and so on. So there may be connection, although for the specific case of the missing satellite problem, I'm not sure whether people really
I know it's a long way from your solution to eventually down to such scale.
Absolutely, that's absolutely right. That if you were to model, I mean, that's what there was some modelization, some n-body simulation, though you can look at the paper. If I find it again, no, it's these papers here by Baldi and Simpson, which have done already simulation of that model, and you will find halo mass functions and things like this, and there are signatures on this that may be connected to any sort of small-scale structure problem of dark matter. But in my model, of course, so there may be a connection between small-scale structure problem and sigma tension. Yes.
And the other question, the second question, is even more extreme case. It's the problem of dwarf galaxies versus globular clusters. I think dwarf galaxies, as you mentioned, they are dominated by dark matter, and actually dark matter even stops star formation.
Right.
On the other hand, globular clusters are the opposite. They are dominated by baryonic matter. It looks like if there was ever dark matter, it kind of escaped. And there is a mass limit, sharp mass limit at about 10 to 6 between those two. And I asked this question to several people, and usually I get an answer, oh, well, they formed differently. But you know, I'm not quite satisfied with that answer, because it looks like in that case, the total mass was too small and dark matter escaped somehow. But this is really loose question in your case.
Yeah. I mean, I've really not thought about this, but I guess maybe could you imagine that because of relative velocities created between dark matter and baryons, you have different formation mechanism for globular clusters and dwarf? Maybe. I don't know, honestly. It's an interesting question. I think all the phenomenology on galactic scale is fairly open for this model. Except for this simulation, I don't really know of the literature that has looked at the connection between dark matter, dark energy interaction, and small scale problems. So unfortunately, I won't be able to answer the question. But yeah, maybe the relative velocity that you create between baryons and dark matter is going to help explaining the differences between globular cluster and dwarf satellites.
Okay, thank you.
Thank you. Muin wrote a question. I don't know if you want to read it or.
Sorry, I don't have the chat here. Can you ask it?
He says, usually S8 is anticorrelated with H0 tension. Is there an intuitive explanation on it?
I think this is true because you're thinking of models that affect omega m. When you think about S8, there's omega m and there's a correlation with H0. I believe that this is where this correlation would come from. But here, I'm really focusing on sigma 8. Omega m is fixed. I'm really focusing on sigma 8. So I don't know if I'm showing H0 in these posteriors. Unfortunately, I'm not showing H0 in these posteriors, but you would see that there are no correlation happening between sigma 8 and H0. H0 is really fixing the background dynamics, and sigma 8 is really just the amplitude of fluctuation. So yeah, I think it's an accidental degeneracy of the fact that we're talking about S8, which involves omega m, which is itself connected to H0.
Okay, thank you. Wang Wei.
Thank you. Okay, Professor Poulin, thank you for your interesting talk. It's very interesting to use a drag between dark energy and dark matter to solve the S8 tension, as the drag doesn't affect the background evolution. However, the constraints of the drag parameters, the capital gamma, and the S8 seems to be loose without the S8. S8 prior.
Absolutely.
Yes. May I ask if their constraints could be more tighter?
Yeah, I mean, here I've used, so you're absolutely right. So another way of saying the constraints are loose means that if you do not know the amplitude of the power suppressions, or to say it otherwise, the CMB does not care in itself about this interaction. But that's not unexpected, because of course, it's something that happens at very late time. So that's what by construction, we know that this is not going to impact the same way. So you could imagine, adding, instead of, I've used F sigma 8 data, and for a specified, I've used F sigma 8 data. You could imagine trying to do more sophisticated treatment of the galaxy, of BOSS data, for instance, and try to constrain this. So yes, there's going to be additional signatures, but if there is a story that makes sense between all the probes, you would expect that as you add low redshift data, not only would the data constrains this interaction rate more, but they would detect it more and more. Yeah.
Okay, thank you.
Thank you.
Anjan?
Yeah. Hi, Vivian. Thank you very much for this wonderful talk. I have just a couple of questions. One is that having your dark energy exactly as a cosmological constant, I think this doesn't work fine. So you need to have some deviation from the cosmological constant.
Absolutely.
Okay. The second part is that what is the, so when you have some dark energy and you coupled with the dark matter, so then what will be your effective dark energy? Means, have you studied that? Means, once you do that, what is the, means when you get the constraint on this, the interaction parameter, what is the effective dark energy? Does it have a phantom crossing or something? Or, I mean, when you do the effective equation of state, it gives a phantom behavior or something? Because what we have studied, that if you have a phantom crossing model, sometimes it can solve both the H0 and S8. So, and that phantom crossing, obviously with a single dark energy, you cannot get a phantom crossing, but sometimes with the interacting dark energy, dark matter model, one can get an effective equation of state that can have a phantom crossing. So will that your model effective equation of state give that kind of some phantom crossing behavior or so?
No, I understand. So in my model, meaning the one that introduced a coupling at the level of the 4 velocities, there is no modification to W. So W is whatever you want based on whatever the potential, if you want, and of the scalar field. If you were to model it as a scalar field, it would be related to whatever you choose for the potential, for instance. But here, really, the interaction only affects perturbations. So the one that may be connected to the question more is the model by Eleonora, or the one that you studied the most. So I don't know. The answer is I don't know whether there is phantom crossing. I mean, actually, I think W in this simple model, if you look at how the equation of state is, it's just a constant. It's just that you fix psi, the new interaction rate, and it's fixed W to be a constant. I guess you could imagine that this psi here is time evolving. Maybe you have a more realistic model, and the interaction rate is time evolving. And then you could create a phantom crossing. But again, in my model, so to say, in the drag term, which is again a model that has been studied way before me, that there is no modification to the equation of state, so you don't have any sort of phantom crossing.
And you can able to write a kind of a Lagrangian that you have said that is there in that paper, that that kind of Lagrangian can give an interaction which doesn't change at all the background equation of state, but exactly. Can give you the momentum. Okay.
Absolutely, exactly. That's the key observation by these guys. Already, you see a while ago, that you have Lagrangians that lead to pure effect at the perturbation level. In fact, even pure effect at the level of the Euler equations, not even in the continuity equation, but only in the Euler, just a momentum exchange. Okay. What is not clear is that the model, which is the one that I studied here, which is like this simple constant interaction rate, this model, exactly this model, is going to be mapped onto this Lagrangian. The coupling might be more complicated, is what I'm saying, but still at the end of the day, what you're going to have is that only the Euler equation is modified. Yeah, and that's that's what they call a type 3 model. So it's fairly generic, yes.
Okay, thank you, Vivian.
You're welcome.
Any other questions?
Now I see the chat. No, it's fine.
Yeah. I have a question. Okay, because the S8 tension is different from the H0 tension, because in one case you have a local measurement. On the other case, the S8 is model dependent. So the problem with our model in the interacting dark energy was that we don't really know how to model the nonlinear scales. So we don't know if it's safe to use the weak lensing data and S8 prior as it is. Okay, so is this some problem that you have?
Oh yeah, absolutely. No, this is, I've completely, so I was trying to argue that first, by the beginning of my talk, that there is hints that large scales are also affected. If large scales are also affected, it means fairly linear scales are also affected, and then sigma 8 may not be too bad as a proxy. But the way I see it personally is just to say, if your model cannot even explain the value of sigma 8, most likely you're going to be, it's not going to work, essentially, is what I'm saying. So I see it as a first thing to do in order to know that's an interesting model. And then you're completely right that doing the things correctly will require confronting to the actual data, which will require maybe redoing simulations, blah, blah, blah. But I think it's just a nice way to get intuitions. But you're absolutely right that using sigma 8 as it is poses a problem because it's extracted from scales that are different, from that requires nonlinear treatment, etc., etc. But that's kind of a generic question, like, should we move on? If sigma 8 is not good, then maybe we should think about moving on to a new way of parameterizing this in a way that is not misleading, because that's the risk, is that if it's not good, is it even misleading towards what I can extract for a model? But yeah, I was trying to argue that because of this fairly large scales probe that we have, there may be a hint that even on large scales you have that, and then maybe sigma 8 is not too bad. But that was, you're right.
No, thank you. Okay, perfect. Do you have any other questions? No? Okay, so thank you so much again for being the first talk of the year.
Yeah, no, of course, it was a pleasure.
Thank
you so much
you
for the invitation, and Happy New Year, everyone.
Okay, thanks a lot again.
Bye.
Thanks, Vivian.
Thank you.
Thank you. See you in a couple of weeks.
Thank you.
Bye.
Bye bye. Thank you.
See you,
Thank
everyone.
you so much.